Before starting with LC, DAD, MS analysis, several routine maintenance operations and check need to be performed. First, we need to check the entire flow path through the system. Namely, every capillary in the system can be disconnected and reconnected in different ways for different purposes, such as maintenance, adaptation for specific purposes, testing and so on. So we need to check whether the configuration is as we need for our analysis. In this case, mobile phase components flow from the reservoirs into the vacuum degasser, then into the pump heads through pressure dampers, then to mixer, then to pressure sensor, to purge valve, from the purge valve into the automated liquid sampler, into the hex valve, then to left heat exchanger, through pre-column filter, through the column, to, then through the post-column heat exchanger, then into the DAD flow cell, and then into MS diverter valve. So all the connections are okay. Additionally, if needed, we can check whether all the connections are tightened sufficiently, otherwise we could have some leaks. Additionally, we can check whether the reservoirs for the waste from the LC and from MS are empty in order to prevent spilling. And finally, we can also check the column. So the column is the one we need for our analysis. It is mounted the right way, so it follows the flow path. With new columns this is not an issue, but with old-fashioned columns they should never be mounted in reverse, since the entrance freight is not dense enough to retain the stationary phase particles. In the case of LC-MS analysis, you should also check support devices. For starters, air compressor and nitrogen generator. Okay, for starters it should be on. It is. In this case we can see that the high duty and service lamps are on, meaning very soon professional maintenance needs to be performed. But for now it should be able to do what we need. Next, rough pump of course works, but we can see there is a lot of oil in the mist filter. We could return this oil into the pump body by opening the gas ballast valve. So now the vacuum will drain the oil back into the pump. When the oil is drained, we should close the gas ballast valve. We should never leave it open, because if someone starts the instrument with the opened gas ballast valve, it can happen that the instrument draws the oil into the MS, which would be very bad. The final thing we could check is the level of oil in the pump. Okay, so the level is quite low, maybe about centimeter above the minimum level, so we should refill the pump. So we start the instrument control software. Of course, all the LC modules need to be physically turned on and allowed to perform the self-test prior to this, otherwise the software will just block. The modules are networked, so they all need to report to their server, in this case diodarate detector, and then DAD needs to report to the software. Network problems can of course occur, but in this case all the modules reported correctly to the software. None is missing and we don't have any error reports. If some of the modules were missing, or if we got an error report, we would need to shut down the software, kill all of its processes, and then restart the module or the entire instrument. In addition to the software, if we have numerous samples, we should also check whether we have enough room on the hard drive. Additionally, the hard drive should be defragmented often, because the heavily fragmented hard drive slows down the data transfer, which can disrupt the communication between the instrument and the computer, and that would break the analysis. Next step is to prepare the mobile phase components. We should use the high purity solvents, such as this one. Components prepared from the non-HPLC grade components, including the ultra pure water, should be filtered through a membrane filter to prevent flow path blocking. Now pay attention that membrane filter has to be compatible with your mobile phase. For example, regenerated cellulose is generally quite stable, but cellulose nitrate should not be used with alcohols, acetonitrile and so on. It will actually dissolve, so it should not be used. The next step is to degas the mobile phase components. Even if there is a vacuum degasser in the system, it is recommendable to degas all the mobile phase components because they can contain large amounts of dissolved air, which could form bubbles in the HPLC system. And if the amount is too high, even the vacuum degasser will not be able to remove it. There are several degassing techniques. In here we use sonication, so treatment with ultrasound. It is not a very efficient method, but in combination with vacuum degassing it is sufficient. Additional point, if a new mobile phase is used that contains inorganic components such as buffers, we should always check whether it can precipitate when it's mixed with the organic phase. So it is done usually in test tubes. We prepare several compositions of the mobile phase containing several different ratios of buffer and organic solvent, and if the precipitation occurs, we cannot use that combination. We may try to reduce the buffer concentration or to change the organic phase. Also, we should make sure that all the mobile phase components are miscible, so we cannot use, for example, water and halogenated solvents because they will not mix. And additional point, for aqueous mobile phases, it may be good to use amber bottles to prevent formation of microorganisms, and also for less stable mobile phases containing some labile organic compounds, it can also be beneficial. So now we can place our reservoirs with mobile phase onto the instrument, but first we should flush the solvent lines and pumps with our mobile phase components. One extremely important note: if we have a solvent line filled with organic solvent, such as this case, we have isopropanol, and we want to use mobile phase that contains some inorganic substance, so some buffer, for example, we should never transfer directly buffer to the solvent line. In that case, buffer will precipitate in the channels and completely block the path. So instead, we should first flush the isopropanol with water and only then add buffer. But in this case, we don't have buffer, just the water. Now, if we transfer the solvent line directly, we would contaminate our mobile phase with the isopropanol. So we will first use just a small amount, up to 50 milliliters, to wash the channel and the frit. We open the purge valve to bypass the column, so now our mobile phase will go directly to the waste, and we set a maximum flow of 5 milliliters per minute in the software. And we start the pump. So we set 100% on channel A to flush that channel with water. We need to wait a bit until the pump starts. And the entire time we should monitor for gas bubbles in the solvent lines. So in the end we should not have any gas bubbles. We also need to check if the pressure in the system is okay. So at the moment it's about 7 bars. If it's above 10 to 20 bars, it would mean that the purge valve frit is blocked, and then we should replace it before continuing. Alright, so far we don't have any bubbles. We can switch to solvent B to 100%. The solvent B is methanol. And we can transfer this solvent line into the main reservoir. We should not touch the tubing that goes into the solvent to prevent contamination. The frit should go to the bottom. Now, if we suspect or if we can see that there is bubbles in the system, we should purge it more, but I think now we can proceed with the next phase. So we shut down the pump and close the purge valve. Never close the purge valve with the flow on, because the pressure will spike. Now we can inform the software about the total available amount of solvent. So it's 120 milliliters of solvent A, and we have half a liter of solvent B. So this way, if the pump runs out of the solvent, it will know beforehand and it will stop the analysis. The adequate volumes of mobile phase to be prepared should be calculated in advance according to the method and number of samples to be analyzed. Of course, we should increase it by a safety factor. Now the pumps are primed. We can tune the MS if needed. So we have to turn on the MS and allow it to stabilize, and afterwards we can run the tune. Okay, now the MS is ready. We can perform the tune. For example, check tune in negative mode. The MS will draw the mix from the appropriate reservoir and calibrate M over Z axis, sensitivities, and some other critical parameters. So after the completed tuning, we can inspect the report and compare it with previous ones, or check if all required parameters are within the prescribed limits. So this way we can detect, for example, if we have contaminations or drops in sensitivity. Now we finally enter or load method to be used. It is advisable to go through all the parameters and inspect them, because there is always a chance another user made, on purpose or accidentally, some changes. We should now equilibrate the column by turning all the modules on. and we will just let the starting mobile phase run through the system for a while. For example, 20 column volumes, that is about 15 to 20 minutes. During the equilibration, we will monitor pressure and detector signals. The pressure will, of course, change as the system is flushed with the new solvent and the column is equilibrated. Do not proceed with the analysis until pressure and all the detector signals are constant. The pressure can be very indicative. If it's unusually high, it indicates flow path blocking, and if it's too low, there may be a leak in the system. So the system is almost equilibrated. You should also check for the pressure ripple. If it's more than 10 to 20 bars, it indicates there is an air bubble in the pump. And in that case, the pump should be purged again. Ripple of about 1 to 2 bars is normal and corresponds to the normal pump piston movement. If using MS, you should also check for MS M/Z assignation, so it should not deviate from integers for more than 0.1 to 0.2 units if we use a low resolution instrument such as quadrupole. If there is significant deviation, we should tune the MS again. If the equilibrium is reached, we can now balance the diodarray detector. And at this point, you should also check instrument for leaks and tighten any loose connections or even replace the faulty fittings. Now the instrument is ready for analysis of samples. We should have our samples ready by now. The samples should be dissolved in the appropriate solvent that ensures solubility, is miscible with mobile phase components, and if we inject large volumes, more than 1 or 2 microliters, it should not be too strong. The samples should be placed into autosampler vials. Before that, they should be filtered through syringe filters. If the sample volume is too low, we should use vial inserts. Otherwise, the sample level will be too low and the sample will not be drawn during injection. The vials should, of course, be compatible to autosampler. The septa should be compatible with the sample. If the sample is photosensitive, we should use amber vials, and we should shut down the autosampler illumination. So we can place our samples into the sampler. Each position is labeled. So this is plate 1, vial A1, plate 1 vial A2, A3, A4, and so on. If using volatile solvents and or long sequences, the autosampler should be cooled down, either using an internal thermostat or, if unavailable, by cooling the lab. We can now prepare a work list. So we configure the most important parameters. Do not forget to include appropriate blanks. And to prepare a vial with washing solvent placed into a defined position in autosampler. We also tend to include a wash solvent and conditioning sample in the work list. So we will include one wash before the work list, one wash at the end, and inject one real sample before our main work list. This sample should saturate the most active sites on the stationary phase, and this data file will be deleted afterwards. After the sequence, we also like to include one injection of solvent and using a method that pumps only the strong phase, in this case methanol, so as to fill the column with just organic solvent. So it's now ready to be stored. The work list should also include safety measures, scripts to be run after the work list is completed, so it will go to standby, and if something goes wrong, so if the sequence is interrupted. So in both cases we will use standby work list, standby script that will shut down pumps, column heater, DAD pumps, and MS nitrogen flow. And now if everything is in order, we start the work list. During the work list run, we can monitor the instrument's behavior for a while. For example, we can inspect the pressure changes during the analysis. We will expect some defined change of pressure, characteristic profile for water and methanol based mobile phase, and if the profile is wrong, that will indicate something is wrong. For example, problems with pumping. After the analysis is completed, we should flush the column with the organic solvent, for example methanol or acetonitrile, without any additives, to wash it from all the sample residues and to prepare it for storage. Now, if the buffers were used for the analysis, to prevent precipitation, we should first purge the aqueous channel with water, flush the column with aqueous organic mobile phase, and only then switch to pure organic phase. Now, during periods of inactivity, the aqueous channel should be kept filled with organic solvent, never with water, because otherwise, after only a few days, algae growth may occur, and of course the instrument will be contaminated. We should also wash the ion source with distilled water. If any solid deposits are formed, some more aggressive treatment may be required, such as sonication or abrasive cleaning.